So there's a couple ways we kind of manipulate logarithmic expressions. There's three main rules. I hesitate to call them the product rule, the quotient rule, and the power rule, because those are names that we also use for derivatives later on, and they're a totally different thing. But we have the logarithmic product rule, the logarithmic quotient rule, the logarithmic power rule. And all it is the following. You have the log of a product is equal to log base b of x plus log base b of y. Thank you. An example of this would be, say, log base 8 of 4 plus log base 8. Sorry, I meant to say log base 2 of 4 plus log base 2 of 8. You can either simplify this as, well, log base 2 of 4 is 2. Log base 2 of 8 is 3. And 2 plus 3 is 5. But you could also combine these as log base 2 of 4 times 8. 4 times 8 is 32. And 2 to what power equals 32? Oh, you guessed it. It's 5. So the point of this is just to see that you can actually add these together by multiplying the arguments, and the result's the same. Totally the same. So let's look at another rule. You have a log of a quotient. It's equal to log base b of x minus log base b. And an example of this could be something like, let's say, log base, don't use 2 again, let's say log base, sure, 2 of, brain 16 minus log base 2 of 8. What's log base 2 of 16, everybody? Yeah, right, because 2 to the 4th power is 16. And what's log base 2 of 8? It's my favorite one. Oh, question. Yes. You're welcome. Log base 2 of 8 is, of course, 3. And 4 minus 3 is 1. Or you could combine these together and say, oh, but that's going to really be log base 2 of 16 divided by 8. 16 divided by 8 is 2. And log base 2 of 2 is 1, because 2 to the 1st power is 2. And then thirdly, we have the power rule for logarithms, which just says if you have log base b of something to a power, that power can come down in front of the logarithm. And so my favorite example of this is something where we actually don't have to calculate things, but you could say, like, what's log base 2 of 7 squared? We're not actually going to get a nice number here, totally fine. But what we're going to see is you could bring this 2 down in front and say it's 2 times log base 2 of 7, but I could also use this first rule and say I really have log base 2 of 7 times 7. But according to the first rule, if I have log of something times something else, it's equal to log base 2 of the first thing plus log base 2 of the second thing. Oh, sorry, thank you. If you add something to itself, like if I said, that is going to be kind of a dumb example. If I said 5 plus 5, what would you say I had? 10, right? But what I'm really looking for is I had 2 times 5, right? Just like if I had x plus x, I'd have 2 times x. If I have something plus something, I have 2 times that something. So if I have log base 2 of 7 plus another log base 2 of 7, I really have 2 times log base 2 of 7. So we can see, oh yeah, the power could have just come down in front. And that's true for any power, right? If I had log base 2 of 7 cubed, that's really log base 2 of 7 times 7 times 7. That's really log base 2 of 7 plus log base 2 of 7 plus log base 2 of 7. But then I have 3 of the same thing added together, so I really have 3 times log base 2 of 7. Yeah, sorry. I know. It's the disadvantage of being zoomed in, but it's good to be able to see the things I'm writing, so definitely be zoomed in. So these are the rules we're going to use. And we're going to use them in both directions, meaning, in fact, which is kind of what I've been doing over here. You might start with something like this and combine it to have one logarithm of the product. Or you might start with a log of a product and break it up into two separate logarithms with each factor. Same thing here. You might start with something like this and go that way. You might start with something like this and go that way. Same thing here. You might start on this side and go that way. You might start with this and bring the a back up as the power. So we want to be able to go back and forth between these equivalent expressions. I'm trying to look over here and see, but it's not over there. So first question here, we want to evaluate 1/2 log base 6 of 81 plus 2 log base 6 of 2. And log base 6 of 81, I don't know what that is. Right? 6 to what power equals 81? We don't know. If it was log base 3 of 81, we would know it was 4, because 3 to the 4th power is 81. But log base 6 of 81, unknown. Well, not unknown, but like not a nice number. Log base 6 of 2, also not a nice number. I don't know what power of 6 gives me 2. It's something gross. It's not 1/3, right? 6 to the 1/3 power is the cube root of 6, which is something different than 2. 6 times 1/3 is 2. Okay, but what we're going to do is we're going to use these rules to kind of, for lack of a better word, compress this logarithmic expression into one small logarithmic expression and hope that it becomes nicer along the way. It does. First, I'm going to bring this 1/2 up as the power. So that 1/2 here is going to come up as the power of 81. And that 2 is going to come up as the power of 2. So I'm going to rewrite this as log base 6 of 81 to the 1/2 power plus log base 6 of 2 squared. And the second part's easy. Log base 6 of 2 squared is just log base 6 of 4. When I say easy, I mean 2 squared is the easy part. The first part's a little bit harder. Log base 6 of 81 to the 1/2. What's 81 to the 1/2? 9, right? Because right, the 1/2 power is another name for the square root. So 81 to the 1/2 power is the square root of 81. So this is log base 6 of 9. Now, separately, these things still aren't very nice. I don't know what log base 6 of 9 or log base 6 of 4 are. But if I put these together using this first rule that you can't see me pointing to up here, I use that rule there and say, I've got this, and I'm going to make it look like that. Log base 6 of 9 plus log base 6 of 4, I should write some equal signs here, is going to equal log base 6 of 9 times 4, which is log base 6 of, let's see, 9 times 4 is 36. And we know what that is. We know that 6 to the 2nd power is 36, so this is equal to 2. I should do one thing here. Give me a little more space to play with. There we go. That's better. Yeah.
So if you're adding the logs, you multiply them, and if you divide it, or excuse me, if you subtract and divide them.
Right. And so I'm going to be a little more specific with the language there, but yes, in general. But specifically, if you're adding the logarithms, you're multiplying the arguments, right? The inside parts.
Right.
And if you're subtracting the logarithms, you're dividing the arguments. What I really want to make clear is you're not multiplying the logs together. It's not log times the other log. It's log of the stuff times the stuff. Or subtracting, it's log of the stuff divided by the stuff. Christian? The logs have to have the same base. Yes, exactly. Other good questions? No, we have terrible. No, so very good questions. Yeah, good clarification. And it can be easy to make mistakes with logarithms, so just be careful as you go. And don't hesitate to ask questions. Hopefully, go to the next page. Do some solving for x. All right. So when we want to solve a logarithmic equation, it's almost always in our best interest to compress the logarithms into one logarithm. Right? We always want one log or maybe one log on each side of the list. Having multiple logarithms is challenging. So I've got log base 5 of x minus 3 plus log base 5 of x plus 1 equal to 1. So I'm going to compress those logarithms using the logarithmic product rule and say that this is going to be log base 5 of x minus 3 times x plus 1. Still equal to 1. So our first step here, compress all the logarithms. Okay, And then we could simplify the insides if it's convenient. And I think it is. So let's simplify the insides and say we've got log base 5 of x squared minus 3x plus x is minus 2x minus 3. Okay, I really want to emphasize here. We don't just get to say the inside part here is equal to 1. I've seen a lot of people want to say that over the years. What we have to remember is we're saying log base 5 of this stuff is equal to 1. That means 5 to the first power equals this stuff. So what we're going to do is we're going to rewrite it as an exponential equation instead of a logarithmic equation. So there's our base 5, there's our power 1, and it's equal to the stuff inside the logarithm. Or another way you could read it is 5 to what power equals x squared minus 2x minus 3? Oh, the power is 1. So 5 to the 1 equals x squared minus 2x minus 3. And now we're solving a quadratic equation, which we have the tools to do. I'm going to bring everything to the right. So 0 equals x squared minus 2x and minus 3 minus 5 is minus 8. And unless someone has done a poor job of writing the question, they usually should factor. And it does. This factors as x minus 4 times x plus 2. Okay, so now we have to be extra. Okay, question.
Sorry, why did we get rid of 5 and where did they come from?
Well, so I didn't get rid of the 5. What did I do to both sides of the equation?
You just added this side.
Well, not added, I subtracted.
Oh.
Right? If I subtract 5 from the left, I get 0. If I subtract 5 from the right, negative 3 minus 5 is
negative
negative.
3.
Yeah, exactly.
Thank you, sorry.
No problem. Ask the question. Everyone wants to know the answer. What are my, well, I'm gonna phrase this. What are my possible solutions here? Right. So my possible, and I'm emphasizing the possible here, my possible solutions are x equal to 4 and x equal to negative 2. But some of these equations might be, these solutions might be extraneous, meaning they're not in the domain of the original expression. If you plug 4 back into the original equation, can we take log base 5 of 4 minus 3? Yeah, log base 5 of 1 is 0. You don't actually need to check the numbers, but I'm just checking. If I plug in 4 here, can I take log base 5 of 4 plus 1? Yes. For sure, log base 5 of 5 is 1. 0 plus 1 equals 1, check. So that's an answer. If I plug in negative 2 right there, negative 2 minus 3 is negative 5. Can we take log base 5 of negative 5? No, we can't take a logarithm of a negative number or 0. If you try plugging that back into the original expression and you get a negative inside the logarithm, you're done. It's not a solution. So the only solution to this logarithmic equation is x equal to 4. And I generally, although I've said this in the past and I've accidentally asked the question that didn't have an extraneous solution, but typically when I ask a logarithmic equation on a test or a quiz, I usually try to make it so there's one extraneous and one not. That doesn't mean that's always guaranteed, right? If you find 2 solutions, they might both be solutions. They might both be extraneous. You might have one extraneous, one for real. So you always have to check them both, even if one of them has already been a solution or not a solution. Let's look at another example. We want to solve 2 log base 3 of x minus log base 3 of x plus 6 equal to 1. And before we can compress these logarithms together, we need to get rid of this coefficient. We really need all of the logarithmic coefficients. Really, I would say to be 1, although if they're all the same, that would also be fine. But 1 is the best. So I'm going to bring this 2 up as the power of x. So I'm going to say I have log base 3 of x squared minus log base 3 of x plus 6 equal to 1. And now, since our logarithms are subtracted, we're going to compress them together by dividing the arguments. So it's going to end up being log base 3 of x squared divided by x plus 6 equal to 1. And then we're going to rewrite it as an exponential equation. My base is 3. My power is 1. It's equal to the argument, which is x squared divided by x plus 6. And then I would probably start solving this by multiplying both sides by the denominator. So I'm going to say 3 times x plus 6 equals x squared. I'm going to distribute the 3 and bring it all to the right. So I'm going to have 3x plus 18 equals x squared. And then 0 equals x squared minus 3x minus 18. I do recommend writing your quadratics or polynomials in general in the way where the highest power of x is first and you go in decreasing order. It's just easy to remember what's what. Like you're not going to mix up your A and B if you're finding a vertex, for example. This one also factors. Factors as, let's see, we're trying to multiply the negative 18 out of the negative 3. I'm looking for a minus 6 and a plus 3. So my possible solutions are x equal to positive 6 and x equal to negative 3. If we plug in 6, we're good to go. Log base 3 of 6 is a totally real number. Log base 3 of 6 plus 6, log base 3 of 12 is also a totally real number. So 6 is fine. On the other hand, negative 3 is not. Log base 3 of negative 3 plus 6 would be fine, right? Negative 3 plus 6 is 3, log base 3 of 3 is 1. But if you plug in negative 3 here, log base 3 of negative 3 is a no. So negative 3 is not a solution. I should point out, I know for both of these examples, the positive number was a solution and the negative number was not. That's not always true. And you can definitely have examples where the negative number is the solution and the positive number is actually extraneous. I'm going to make something up. It's not going to be exactly right, but just for a second, let's pretend here's an equation we're not going to actually solve, but let's say we had something like this. Log base 3 of 4 minus x plus log base 3 of 9 minus x equals 2. I'm not actually finding the solutions or saying these are solutions, but let's pretend our possible solutions were x equal to negative 3 and x equal to positive 6. We can see that if we plug in negative 3, that's okay. 4 minus negative 3 is 7. We can take the log of 7. 9 minus negative 3 is 12. We can take the log base 3 of 12. Probably doesn't actually add up to 2. That's all right. On the other hand, 6 is no, right? If you plug in 6, log base 3 of 4 minus 6 is log base 3 of negative 2, and that's not going to work. So if these were the solutions to this equation, I should say the possible solutions, 6 would be not a solution and negative 3 would be a solution. So I just don't want you to sit in the place where you think, oh, it's always the negative ones that don't work and the positive ones that do work. You have to plug them back into the original expression to see if you're taking the log of a negative. Christian.
Does it have to equal what it says it equals?
Yeah, so this equation isn't right. I made something up that's not actually true. Just to point out that if these were your solutions, that this one would be the one that's valid and this one would not be. But these are definitely not actual solutions. Okay. If we have time, we'll do a couple more. So let's look at some of this. Solving for x, log base 8 of 32 equals x. So I will say there's kind of, there's kind of two flavors of solving logarithmic and exponential equations. One flavor is where kind of everything has a common base. That's going to be the flavor here. 8 and 32 both have 2 as a base. They're both powers of 2. Right? 8 is 2 cubed, 32 is 2 to the 5th. The other flavor is where things don't have a common base, like the next equation, right? 10 and 2 do not have a common base. They're not both powers of the same number. They're both multiples of 2, but they're not both powers of 2. So, and that's gonna result in a less nice looking answer. Whereas the ones where you have a base in common, typically you're able to end up with a pretty nice looking answer. So how do we solve this? Well, we're going to rewrite it. We're going to rewrite as an exponential. That is 9 times out of 10 what I'm going to do with a logarithmic equation or expression. Is I'm going to rewrite it as an exponential expression. So I'm going to rewrite this as 8 to the x equal to 32. And then if we can see that there is a common base, we're going to write both sides as powers of that common base. So 8 is 2 cubed to the x, and 32 is 2 to the 5th. And then we can simplify the left-hand side using our rules of exponents. When you have a power to a power, you multiply the power. So you have 2 to the 3x equals 2 to the 5th. And then once the bases are actually the same, you get to conclude that the exponents have to equal each other. So 3x has to equal 5. So x has to equal 5/3. There's no need to check this answer here because the thing we're finding wasn't already in a logarithm. Right? There's no out of bounds here. There are other ways to solve this. There's something called the change of base formula for logarithms that would also totally be valid here. But that's not the point of today. So as much as I would like to talk about it, it's not where we're really going. Any other questions? Okay. No. All right. Oh, sorry. It's Friday's quiz based off of notes / homework for E and F. Yeah, and I would also say D as well. So typically like the previous 3 things we've done, like so the previous Friday, the Monday, and the Wednesday, I think are what are like fair game for the quiz. That said, right, as with most math classes, things build upon other things. So even though we might not be explicitly saying homework A, B, and C are on the quiz, there's still things that I could ask you that would kind of incorporate those. So they're maybe cumulative-ish, but focused on the most recent stuff. Yeah.
Will there be a practice quiz?
There hopefully will be a practice, but my intention is always to have a practice quiz up there. It's just I have to write them. So
Right.
yeah. Yes, that's the plan, and I'll try to get that up today sometime. Yeah, today. All right. So 10 to the x equals 2. There's not a lot to do here. I'm going to rewrite it. Well, I'm going to try and solve for x. I could rewrite it as a logarithmic equation. So as a logarithm, what's my base? 10. What am I taking the logarithm of? Or better, no, better question. What's the logarithm equal to? X, right? Because the logarithm is the exponent. Right, I know x is not the same. Let's start with that. Right, the logarithm is the exponent. So whoops. Good thing it was all sealed up there. If you're ever not sure what you're saying the logarithm equal to, just remember the logarithm should be equal to whatever the power is. So here I see 10 to the x. Oh, the logarithm is the x. And then, well, the only thing left is the 2. And that's kind of all we can do. I will point out, since it's log base 10, we would usually abbreviate this as x equal to just log of 2. Right, if you don't see a base, the base that everyone means is base 10. And that's all we can do. If someone asked you for a decimal approximation, you could pull out a calculator and get a decimal approximation. I don't know what it is. So I know it's either 0.7 or something else, 0.3, but I don't actually remember. So I'm not going to write down something that's wrong. And that's not really the point. I don't care that it's approximately whatever. I care that you're able to solve for x. Yeah, question.
So what happens to 10?
What happened to the 10 is we got lazy. No, for real. Like that's what's going on there. Is log base 10 is such a frequent occurrence. Right? There's a button for it on your calculator. Right? There's an LN button and an LOG button, and there really aren't any other bases on your calculator unless you have like calculator with all the buttons that has like a log base x of y. But log base 10 and natural log base e are the most common bases we encounter. And since we encounter them so much, I mean, it's also like a typesetting thing. People are trying to save in. They're not going to write all those 10s if we don't have to. But really, it's just an abbreviation. So
Just for the 10 or like?
just for the 10. And I will also point out, and there's another abbreviation as well. Log base E of, I don't really care what, say 3, is the natural log of E. Again, nothing special, just an abbreviation. And if you don't like this, it is perfectly fine to, whenever you see this, rewrite it as log base 10. It is totally legitimate to rewrite it every single time you see it. You're going to get tired of doing it, but you can. Similarly, whenever you see ln or natural log of E, oh, sorry, sorry, that's a natural log of 3, apologies. Right, the argument shouldn't change for no good reason there. But whenever you see a natural log of something, it is perfectly legitimate to rewrite it as the log base E of the same something. So just abbreviations, nothing else. Question, yeah, Erica.
What is the E?
So E is a number. What's pi, approximately?
3.1.
Thank you. E is the same kind of deal. It's about 2.7. It's one of those constants that is super duper important. So pi, you get pi because it's the ratio of the circle's circumference to its diameter. And for any circle, the circumference divided by the diameter is pi. E is a special number that we'll actually talk more about later. There's a couple ways of finding it, but one way of finding it is as it is kind of as a limiting value of this, what's it called? Words of the, oh my God, interest. There's an, like when you're getting money, compound interest, thank you. There's a compound interest formula. I know, right, thank you. So when you talk about compound interest, which we will in a couple classes here, there's this formula for it where you like, if you compound interest so many times per year, you plug in all these things. And the thing is that if you compound the interest more and more frequently, the number that ends up kind of popping up due to that is the number. So it's a very kind of important number in all sorts of financial systems and mathematics everywhere. We'll definitely talk more about it. But yeah, as far as we're concerned, and what you should really take away right now is that E is about 2.7. That's really all I ever remember about it. Well, that's not true, but like, okay. So what about this next equation? E to the x equals 10 to the x plus 1. So now we've got a situation where we have exponents on both sides. We could rewrite it as a logarithmic equation, right? It would totally be fine to say, well, I'm going to take E as my base. So I'm going to rewrite it as log base E of what? Well, let's skip that part and set it equal to the exponent. Log base E of something should equal which exponent? X, right? The exponent that was on the base we're using. And then the stuff has to be 10 to the x plus 1. Okay, that's all right. Now we can bring down the x plus 1, right? We're going to use that power rule. You've got the logarithm of something to a power. I'm going to bring down the power as x plus 1 parentheses times. I would really much rather write the natural log of 10 as opposed to, well, I mean, it is the natural log of 10. I'm just going to write the abbreviation. But I'll just remind everybody that's still just log base E of 10. And then we want to solve for x. So to be able to solve for x, I really have to distribute the natural log of 10 to the x plus 1. So I'm going to get x times natural log of 10 plus 1 times natural log of 10 equal to x. And then I'm going to bring all the x's to the same side. So let's bring them all to the right. So I'm going to have a 1 times natural log of 10 still on the left, or just natural log of 10, equal to x minus the thing I'm bringing over to the right. So x. I'm going to factor out an x. I'm going to factor out the x I'm left with. a 1 from there, and a minus natural log of 10 from there. Finally, I'm going to divide both sides by the 1 minus natural log of 10. So that x is equal to the natural log of 10 divided by 1 minus the natural log. And if you care, not that I really care, but if you wanted to know, this is approximately what negative 1.77. Question, Lee. So one more time, sorry. From here to here?
No, from there to the last step.
From there to there? Sure. So what I did from here to here was I divided both sides by this coefficient. So I took the natural log of 10 equal to x times 1 minus the natural log of 10, and divided both sides by 1 minus the natural log of 10. And these cancel out. Because although it's not a nice number, 1 minus the natural log of 10 is just a number, right? I mean, I don't know what it is, but it's something, it's some negative number. It's probably like negative 1 point something. Time. Let me look. How much stuff I got? Yeah, okay. We're all right. So what?
Is that the result?
That is the result. Yes. So this would be our final answer. And I will stress here, you do want to leave your answer as this, unless someone specifically asks you for a decimal approximation. You should be writing your answer as what's called an exact answer. It's kind of like the difference between writing your answer as square root of 2 and 1.4. Right? Square root of 2 is exact. It means 1.4, all the other numbers forever, whereas 1.4 is just an approximation of that number. So exact answers are like this and like square root of 2. Decimal approximations are not usually what we're looking for, but some of the times you do ask. So, something else I want to say about this. So while we did this a perfectly fine way, there is a more kind of, I don't know, standard way of actually doing this question. So I want to kind of show it to you again, just so you can see the way people actually usually solve this. Let's go ahead and not have an extra paper up here. Fine. Everything's got numbers on it already. Sorry. So here's the way most people would probably actually go about solving this. You have e to the x equal to 10 to the x plus 1. The typical kind of step that most people make first whenever you're solving an exponential equation is to take the natural log of those sides. Why the natural log? Because it requires the least amount of writing. It's 2 letters versus 3 letters and a base. Also because it's like the most common log of a base, but also because we're lazy. So I've got the natural log of e to the x equals the natural log of 10 to the x plus 1. Then we're going to use the power rule. We're going to bring down those powers. So bring down the x. You get x. In fact, let me just show you. Yeah. That gets to come down in front. You have x times the natural log of e equal to x plus 1 parentheses times the natural log of 10. You make sure that when if your exponent that you're bringing down has more than one term, you put parentheses around it so that all of it's getting multiplied by the natural log of whatever that base is. All right, so who wants to be brave and tell me what the natural log of e is? Oh, sorry, there's a question there. Sorry. I'll address the grade scope question a little bit later there. But yeah, sorry, I'll look at that. Sorry, so everybody, somebody who wants to tell me or show me on your fingers, what's the natural log of e?
1.
Thanks. Yeah. And just show me on your fingers. So exactly 1, because the base is e, and e to the first power is equal to e. I know we didn't write the base, but right, you could also say, oh yeah, that's log base e of e. So we really have the same equation as before. X equals, I'm going to distribute that, x times the natural log of 10 plus the natural log of 10. And then I'm going to subtract so I can have all the x things on the same side. So x minus x natural log of 10 equals natural log of 10. I factor out the x on the left. I'm left with a 1 minus natural log of 10. And then finally, I divide both sides by the coefficient of x. So I end up with x equal to the same thing as before. The natural log of 10 over 1 minus the natural log of 10. So either way is perfectly fine, but I felt like I owed you seeing it this way because this is definitely the more typical way of solving an equation like this. Yeah.
On both, make the solving it, how do you get from like, x minus x L and 10? So
Yes.
like x is 1 now.
Sure. So what I've done is I've factored out the x, or if you want to think about it, I've divided out the x. So when I really, right, if you look at x minus x times natural log of 10, this is really x times 1 minus x times natural log of 10. And I'm dividing out the x from each term. I'm left with a 1 there and a natural log of 10 there. But if I were to distribute it back through, I'd get the same thing. X times 1 would give me the x times 1, and x times negative natural log of 10 would give me negative x times natural log of 10. That's what's happening there. Other questions? Oh, sorry, didn't see it.
So could I find any equation that looks like exponent equal to another exponent to an maximum?
Yes, yes. So, and what time is it? Yeah, we got time. I think we got time. Well, I think we have a couple here. Yeah, there's one at the end. So we'll do an example. Let's look at these first ones. So solve some of these easier ones. I always feel like it's weird when the base is a variable. Like that's a less typical type of question, but it's still the same sort of process. We're going to rewrite this as an exponential. So I've got x raised to the negative 3/2 power equals 27. So if I want to solve this, if I'm trying to isolate x, I want the power on x really to be 1. If you want x by itself, you really have x to the first, right? We don't usually write it because it's annoying, but we're looking at x to the first. So if I want to kind of get rid of this power, what we're going to do is we're going to raise both sides to the reciprocal power. The sign should still be the same. So the reciprocal of a number is the same sign as the original number. Positive is positive, it's negative is negative. That means we also have to do it to the other side. And then the reason we did that is because when you have a power to a power, you multiply the powers. And negative 3/2 times negative 2/3, that's just 1. And 27 to the negative 2/3, I'm going to deal with firstly by writing it as 1 over 27 to the positive 2/3. I often kind of like to get rid of the negative power part by bringing it down to the place where it's not. So if it's in the denominator, bring it to the numerator. If it's in the numerator, bring it to the denominator and change the sign of the power. Do be careful though. I haven't seen really anyone do this yet, but I know I've seen lots of in the past. People really want to make like a fractional power a negative power. Like they want to say that the 1/3 power is the same as the negative third power. They're not the same. Right? 1/3 means cube root, whereas the negative third power, actually the 1/3 power means the cube root. Whereas the negative third power means you are doing the reciprocal of your thing to the third power. So very, very different. In any case, 27 to the 2/3. We have kind of two directions we can go here. I could either do the numerator part of the power first or the denominator part of the power first. And you know me, well, maybe you don't, but you're going to know me. You know me, I always want to do the denominator part first because it's usually going to make things easier. Here's what I mean. I mean, we should do 27 to the 1/3 squared instead of 27 squared to the 1/3. Because we don't know. Well, I mean, you might know. You might have done it enough times right now that you know. We probably don't know what 27 squared is. We definitely probably know what 27 to the 1/3 is. What's the cube root of 27? Right. So we get 1/3 squared, and we know what 3 squared is. 3 squared is 9. So we get 1/9. On the other hand, if you did it as 27 squared and then took the cube root of it, you would also get 9. It's just 27 squared is 729. And the cube root of 729, you probably need a calculator to see that that's actually 9. It is, but this is the easier path. Okay, so let's do another one. Well, a different one. Let's see if I write myself any notes about this before we get going here. Nope, okay. So for this next one, I think your question is very pertinent here. I'm trying to solve this. So here's what I would say. If you don't have an exponent on both sides, you're perfectly good to use the convenient base that's already there. So for this one, I really want to rewrite this as a logarithmic equation with what base? Base 5. Because 5 is the thing that's being raised to a power. So we can totally rewrite this as log base 5 of, well, I know it's equal to the exponents. What's that? Yeah, totally. So what I'm doing there is I'm skipping that part just because I'm kind of pretending like I'm not sure what goes in there, but I know that the logarithm always should equal the exponent. So after I figure out those two parts, I know the base, I know it equals the exponent. The last thing that's left has to get filled in there. And then you can solve for x. So log base 5 of 4 plus 3 equals 2x. And then divide the whole thing by 2. Log base 5 of 4 plus 3 divided by 2 equals x. Now, just so you guys know, even though this is probably the nicest way to solve this, there is kind of an issue here. If you wanted to actually approximate this with a calculator, most calculators don't have a log base 5 button. Most calculators have a natural log button and a log base 10. So a lot of times people solve this instead of using log base 5, they actually just start by taking the natural log of those sides. So an alternative way to solve this, we just say the natural log of 5 to the 2x minus 3 equals the natural log of 4. I should mention before we do this, I'm perfectly fine with you solving this either of these ways, or really any kind of way that is correct, right? If you know what you're doing here and how to solve these things, you can use whatever route you want to get there. Natural log of 5 to a power, I'm going to bring down the power. So 2x minus 3 times the natural log of 5 equal to the natural log of 4. Now I'm trying to solve for x here. One option would be to distribute and then just, but I think it's going to be nicer if we just divide by natural log of 5. So 2x minus 3 equals the natural log of 4 divided by the natural log of 5. And here's a place where it'd be easy to make a mistake and try and compress this in some way that we can't. This doesn't compress. Right? This is not the natural log of 4/5, because that would be the natural log of 4 minus the natural log of 5. It's the natural log of 4 divided by the natural log of 5. And you can't simplify a division of natural logs. It just is what it is. And then we can solve for x. So I'm going to get 2x equal to the natural log of 4 divided by the natural log of 5 plus 3. And then finally, I should have left myself a little more room here. Look at this way. X would be the natural log of 4 divided by the natural log of 5 plus 3, all divided by 2. 2. So virtually the same thing as before. It just looks a little bit different. The real difference here is that instead of writing log base 5 of 4, I'm writing the equivalent thing, which is natural log of 4 divided by natural log of 5. Either way is fine. I will point out that if I was really solving it this way, I probably wouldn't have a fraction and fraction. I probably would have said instead x equals 1/2 times the natural log of 4 over the natural log of 5 plus 1/2 of 3. If I would write an answer like that. But really, any of these is fine. So generally, you can solve exponential equations by either rewriting them, rewriting them as logarithmic equations like we did here, or by starting by taking the natural log of both sides. Or really, you could take the log base whatever you want of both sides. It is just fairly standard practice to use for natural log. Okay, look at this last example. So 3 to the x plus 1 equals 5 to the 2x. Now here, you probably do just want to use the natural log. You could use base 3 or base 5, but it's really kind of most typical to use natural log here. So I'm going to do the natural log of both sides. And again, really it's because I have exponents on both sides of this equation. It's going to get a little messy. The first step, well, I should say the second step, right? The first step was taking the natural log of both sides. The second step is going to be bringing down those powers. So we're going to have x plus 1 times natural log of 3 equal to 2x times natural log of 5. Now, I should be more careful than that. If I was being not very careful, I might think I just had x plus just a 1 times natural log of 3. But we know there should actually be parentheses around that, and all of that power should get multiplied by the natural log of 3. In other words, we distribute the natural log of 3 to each of those terms. Our kind of overarching goal here is to get all the x terms on the same side so that we can factor out an x and solve for x. So I'm going to distribute that. We get x times the natural log of 3 plus 1 times the natural log of 3. Excuse me. So let's write as natural log of 3 equals 2x times natural log of 5. And then since I already have an x on the right and I don't have any not x things on the right, I'm going to bring this x term over to the right. So I'm going to rewrite this as the natural log of 3 equals 2x times the natural log of 5 minus x times the natural log of 3. Okay. Now we have all the things on the right with an x. What are we going to do next? What do we do after we have all the x's? Well, let's see. Let's look back over here. So you're right. You're just not using the word I was hoping to hear. Starts with an F. We're going to factor out the x's. But exactly. We're going to say, oh yeah, I don't want that x in there. So I think you all should write down what's left after we factor out. You got a minute still. I can take my time. So you should all be writing the thing that goes in here. I'm going to sneeze and it's going to be terrible. Don't sneeze. It's like we're the worst because, like, you know, the feeling when you want to sneeze. And I want to sneeze. I hate not sneezing when you want to sneeze, but also sneezing with a mask on is kind of awful. So, all right. So if we divide out or factor out an x, we're left with a 2 times natural log of 5 minus natural log of 3. And then the last step here is to divide both sides by whatever is multiplying x. So we've got natural log of 3 equal to x times this kind of gross thing here. And then we're just going to divide both sides by 2 natural log of 5 minus natural log of 3. And then those cancel on that side. So we end up with x equal to the natural log of 3 over 2 times the natural log of 5 minus the natural log of 3. And although there is some minor simplification people can do on this, you shouldn't. So, oh, sorry. So I've definitely seen people in the past rewrite the denominator as like the natural log of 5 squared minus the natural log of 3, and then write it as the natural log of 25/3. Don't do that. It's perfectly fine if you do that, but it's not necessary. So don't spend your time on that one. There's other more important things.
Would be 7, 3, cancel out?
No, they cannot cancel. So we can only cancel things in the numerator and denominator. Essentially what we're saying here is, so let me ask you, actually, that's a good question. I really feel like I should take just a second to say something about. Let me ask you guys this. If I had like, let me make up a fraction that works well. 3 over 3 plus 9. 3 over 3 plus 9 is 3 over 12, which reduces to 1/4. Can I cancel those 3's? No, because if I did, what would I get? Well, you might say 1 over 9, you might say 0 over 9. Either way, it's not going to be 1/4. So we can only, but so let me point out though, you totally could factor out a 3 from the bottom. And then that 3 that is now multiplying everything else totally can cancel, because 3 divided by 3 is 1 there. And you get 1 over 1 plus 3, which is 1/4. So you can only cancel things in the fraction if you can factor them out from both the top and the bottom. So I'm really factoring out a 3 from the top, right? So 3 times a 1, and factoring out a 3 from the bottom, it's a 3 times 1. But we can't do that in the other expression, so no, we can't cancel.